Hello! Welcome to another Introduction to Astronomy lecture. This lecture is lecture number 11, and we will be talking about the Sun. In today's lecture, we will learn about how the Sun is rather an ordinary average star as far as all stars go. We will also talk about the Sun's composition and the various states of matter that occur within the Sun. And we'll talk about the layers, the innermost and the outermost, and also about how there's solar activity on the surface and the magnetic field gives rise to a lot of interesting phenomenon, such as space weather and how it affects the planet Earth. So our sun is, as we know, located at one of the focal points in the solar system and within the elliptical orbits of all the planets in the solar system. And it is quite an ordinary star as far as all the stars in the universe go. It's neither too hot nor too cold. It's not too old or too young. And it's not too large or too small. This is Goldilocks' star, if you will. It's overall pretty average. And from what we know about our comparative planetology methods, well, we can use our comparative methods for our sun to look at other stars in the universe since it's pretty average. This is very beneficial. But despite it being a rather average star, we will learn that our sun is very complicated, extremely dynamic, and it is a lot more so than any of the planets we've studied so far. Through the use of spectroscopy, astronomers have been able to deduce the composition of our sun. They have found that 73% of its mass is hydrogen, while 25% of its mass is helium. The remaining percentages are made up of the more familiar elements like oxygen, nitrogen, and carbon, make up about 2%. And then the heavier compounds like silicon and aluminum, which are very present here in the terrestrial worlds, are minute in the sun, composing only 0.1% of the sun's mass. So a star is typically composed of hydrogen and helium predominantly, and this wasn't actually known until about 1925, thanks to Cecilia Payne-Gaposchkin during her PhD thesis. Originally, her idea was rejected because the popular opinion at the time was that the sun would be composed of the same things as the Earth. It was just hotter. However, she found that it was composed of all of these elements which we have discussed. And it still took a few years for astronomers to acknowledge that the Earth was abundantly composed of the rare elements, while most of the universe was actually hydrogen and helium. Previously in this course, we talked about how Jupiter had a composition of hydrogen and helium, and how in its core it had metallic hydrogen due to the enormous densities there. However, the Sun is too dense and too hot for metallic hydrogen to exist in its core, because at this point, nuclear reactions begin to occur. So, due to these reactions, our sun is incredibly hot, and all of the inner elements are in a unique form of gaseous atoms because there are no solids or liquids that can exist at these temperatures, at this level of heat. Many of the electrons that would normally be bound to the nuclei of the atoms have been stripped away from their nuclei and are flowing freely around. And this is a state known as ionization. The gas is ionized. And in this hot electrically charged state of gaseous atoms is what scientists call a plasma. So you may not be super familiar with plasma, but it is one of the other states of matter. So we are familiar with solids, we eat solid food, we drink liquid water, and we breathe gaseous air. However, we don't really see plasma except in lightning strikes or if you accidentally microwave metal. Or if you are looking at the sun. However, I would advise you not to look at the sun unless you have proper protective eye gear. Please don't look at the sun. But ionized gases are incredibly difficult to measure or to look at spectroscopically because the absorption and emission lines that we look at for those nuclei are much fainter. So measurements have to be made very carefully. So now that we know more about plasma, we can talk about the inner layers of the sun. The sun's inner layers are divided into distinct layers. So the innermost is the core, which is the densest. It is extremely dense, and it makes up 20% of the size of the sun. And it is a region where the plasma is the source of all the nuclear energy, and it is incredibly hot, reaching nearly 15 million degrees Kelvin, which is nearly 27 million degrees Fahrenheit. Outside of the core is the radiative zone, where the light energy being released from the core due to the fusion is slowly transferring out through radiative reactions. So the photons being released from the nuclear fusion in the core are being absorbed and re-emitted throughout this radiative zone. However, it's so dense that the light is actually traveling very slowly in terms of making its way out of the radiative zone. It's still traveling pretty fast, but it's absorbed incredibly quickly as well. So this process is very slow, and it is a very large size of the sun, which is anywhere from 25% to 70% of the sun's size. Outside the radiative zone is the convection zone, where energy is transported from the radiative boundary to the surface in convection cells. So this thick layer transfers plasma in those convection cells from the bottom of the convection zone up to the top, where they come out as like bubbles. And this is where it releases the heat out into outer space, and a lot of the energy is then sent back out into space. But these bubbles then sink back down to the edge of the radiative zone. So it's like a very like scooping process. It's similar to um, bubbles rising in when you're boiling water. So now we can talk about the outer layers of the sun, which are divided into the photosphere, the chromosphere, the transition region, and the corona. So the outer atmosphere of the sun is overall transparent, while the inner layers are blocked visually by the opaque photosphere. Energy is transferred through the inner layers of the sun very slowly, as we talked about, with the photons being absorbed very quickly. And so only once they reach the photosphere can they escape and be released out into space. We observe that the photosphere has this, when we look at it with telescopes and very sensitive equipment that is, again, safe to look at the sun. Please do not look at the sun. We observe that the photosphere has a really mottled appearance. This is what we call granulation, and this is very similar to the bubbles rising up on the in boiling water. That constant turbulent motion on the surface is a lot like on our sun. And these granules only last about 5 to 10 minutes. However, there are sometimes much larger ones called supergranules, which can be 35 times the diameter of normal granules, and they can last up to 24 hours. And we can study the motions of these granules in the photosphere by looking at the Doppler shifts of the surrounding gas. And so granules from hotter columns of rising gas will brighten when they travel upwards, and then as they lose energy, they drop back into the opaque regions from after they cool on the surface of the photosphere. So the hot stuff rises up, releases its energy out into space, and then it drops down because it's cooler. So that's this convection cycle that we have. So now we can talk about the chromosphere, the next layer in the outer layers of the sun. It wasn't until the past century that the chromosphere was actually visible because we needed a total solar eclipse to be able to see it. This layer appeared as narrow streaks around the edge of the moon during the solar eclipse, and so it only lasted for a brief moment when everything was lined up that we could then see the photosphere because we could see the chromosphere because we needed the photosphere completely blocked. And this is why the chromosphere has the Greek name colored sphere. The chromosphere is approximately 2 to 3,000 kilometers thick, with bright emission spectra of hot gases that are generally red and yellow in wavelength. Red is one of the largest emission wavelengths in the visible spectrum, which is caused by hydrogen. In 1868, the unusual yellow emission line was seen, which didn't correspond to a known element at the time, and that element was then named helium, and it wasn't until 1895 that helium was then discovered here on Earth. Helium being based on the Greek word helios, because it was discovered in the sun first. And the chromosphere is approximately 10,000 Kelvin, which is hotter than the photosphere. And this is surprising because it's a surprising characteristic of the transfer that energy goes through in the outer atmosphere. The chromosphere isn't the only region in the outer parts of the sun's atmosphere where the temperature increases. We find that the transition region, the temperature increases dramatically up until the cusp of the corona, where the temperature then still increases, but not as much. We can see in the graph down below the temperature increasing, how it dips down in the photosphere, rises again in the chromosphere, and then shoots up crazy high in the transition region, and then slowly tapers off in the corona. So it wasn't until 2013 that we had these measurements, which were taken by NASA's Interface Region Imaging Spectrograph (IRIS), which concluded that the sun's atmosphere is incredibly complex and way more so than we initially imagined. The outermost layer of the sun's atmosphere is called the corona, and it's been studied for centuries since it extends millions of kilometers above the photosphere because it's very extensive and diffuse. And so while the corona is best visible during the total eclipse, it can be studied by orbiting spacecraft using a special instrument known as a coronagraph, which removes the glare of the sun and then allows it to study the fainter regions around it. So I think the best analogy for a coronagraph is if you are driving looking towards the sun and you need to see oncoming traffic. So you put your hand up or you bring down your visor to block out the sunlight, and then you can see the light around your field of view much better because you have blocked out the intense light of the sun. So that's what a coronagraph is doing. It's blocking out the intense central light of the sun so that you can see the more less intense, more diffuse light surrounding it. Spectrographic studies of the corona have shown that it is very low in density, being at only 10 to the 9 atoms per cubic centimeter nearest to the sun, compared to 10 to the 16 atoms per cubic centimeter in the upper photosphere, where the atmosphere starts to begin to become opaque. So, in addition to light, the sun is constantly emitting a stream of charged particles, which we call the solar wind. The solar wind is formed by rapidly moving particles which cannot be contained by the sun's gravitational field, and they escape at nearly 400 kilometers per second, with nearly 10 million tons of material being lost from the sun every year in the form of solar wind. That still doesn't put a dent in it. The charged particles emerge from dark areas, which are relatively cool regions in the sun's corona called coronal holes. And within these coronal holes, it's the sun's magnetic field, which is pointing outwards and then curving back to the surface, which has streaming particles along those field lines. On Earth, we are shielded from the solar wind by our atmosphere, but near our poles, these charged particles from the solar wind interact with our atmosphere and produce glowing streams of light, which we call aurora. If you were fortunate enough to look outside, it was actually quite a few months ago, but we did have a faint auroral glow visible here in Tallahassee because the sun goes through periods of activity and is currently very active. So now we can talk about sunspots. You may have heard of sunspots before. They are these darker regions on the sun, which are little spots. And so they are caused by increased areas of magnetic field activity on the surface. So they appear darker because of their cooler temperature relative to the regions around them, but they are still incredibly hot and hotter than the surface of many smaller stars. So sunspots can have a diameter of over 140,000 kilometers, and their lifetimes vary from a few hours to several months. But they don't stay in the same place because the sun is not a rigid body. It's made of plasma, as we've talked about. And the sun rotates at different rates along different parts of it. So this is what we call differential rotation. And so sunspots at different parts of the sun rotate around at different speeds. In the 1800s, Heinrich Schwab showed that the number of sunspots on the sun actually vary systematically in decade-long cycles, which are called sunspot cycles. And when you plot them out on a graph like latitude versus longitude, you get these patterns, which are called butterfly plots. Schwab determined, though, that although individual sunspots vary, there are periods of time, which is roughly every 11 years, or 9 to 14 years. It depends. Uh, when the number of sunspots are at a maximum, this is called a sunspot maximum. And then there are intermittent periods of times where there are less sunspots, called a sunspot minimum, or solar minimum, or solar maximum. We are currently close to, I think we are maybe just after solar maximum, or we are nearing it. So there is still quite a lot of sunspot activity on the sun, which means that solar weather is quite active. And so I will let you guys know if there are any upcoming aurora potentials. These cyclic changes in the sun aren't random, but happen due to the changes in the sun's magnetic field. We measure the sun's magnetic field by what's known as the Zeeman effect. And this is when atoms in the presence of a strong magnetic field are not precise, don't have precisely defined spectral lines, but instead several smaller, narrower levels which are smeared across the energy levels. This Zeeman line smearing in discrete bands is proportional to the strength of the magnetic field and occur relative to sunspot cycles. We see more fluctuations and changing polarity of the magnetic field. So, unlike the planets, which have relatively stable magnetic fields, the sun's is very strong and very complex. This magnetic field occurs to the turbulent movement of the ionized gases in plasma in the convection and radiation zones, which gives rise to what we call a dynamo effect. These convections are difficult, if not impossible, for scientists to model, and so the resulting solar cycles occur, understanding why these solar cycles occur exactly is an ongoing question. We can kind of map out the regularity, but coming up with a theory that explains all of our observations is still quite difficult to come up with for the exact ways in which plasma interacts with the magnetic field and these convection layers and radiative zones interact. It's very complex and computationally intensive. Similar to sunspots, but hotter, are these things called plages. So when we look at the sun in calcium and hydrogen emission narrow bands, we see that there are bright clouds in the chromosphere known as plages, which correspond to higher temperatures, which these areas then surround sunspots. So the cooler regions, the sunspots, are surrounded by hotter areas in the chromosphere. Higher in the sun's atmosphere, we have prominences, which are originating from these sunspots and are these great looping bands, and they are best viewed from the side. So, particularly during solar eclipses, when the sun is blocked out by the moon, we can see sometimes these prominences as these looping features, these red arcs going across the surface of the sun. And sometimes they reach out into the corona. There are three types of prominences. There's quiescent, which are loops of plasma that are in stable emission for several hours or even days. There's eruptive prominences, where matter is sent quickly out into the corona and is very abrupt, can be very just a short burst. And then there's surge prominences, which are the most intense and active and the fastest moving with speeds of up to 1,300 kilometers per second. So that material is being shot out into space. The most violent types of prominence events are known as solar flares. They are very short and last about 5 to 10 minutes, and they emit a huge amount of energy equivalent to nearly a million hydrogen bombs, all being released at once. So the largest flares can last actually several hours with enough energy released to power the entire United States. And it's during sunspot maximums that small flares can occur several times a day. Matter associated with a flare is heated up to 10 to the sixth Kelvin, so nearly a million degrees Kelvin, which then floods space with X ray and ultraviolet radiation. Often, these flares disrupt the surrounding corona and they eject material into what we call interplanetary space in an ejection that we call a coronal mass ejection, a CME. Since these surface activities are correlated to high magnetic fields and sunspot cycles near solar maximum regions, we call these areas active regions. Astronomers try to predict when activities are much higher in frequency and magnitude because we need to know potentially if something big is heading our way, which could affect electronics here on Earth, or more likely just to put our satellites in orbit into safe standby modes. So the sun is constantly emitting charged particles at us, and these CMEs can actually have big effects here on Earth. So this wasn't a field of research that was really known until what was called the Carrington event. In 1859, after an observed solar flare, and nearly a day later, there was a significant solar storm that reached Earth that resulted in the northern lights being seen down near the equator and telegraph lines actually having sparks and catching fire where there was exposed wires. So now our world is much more technologic and electronic and much more dependent on electronics. So being aware and having predictive models to predict when there are going to be significant events is crucial. However, predictability is poor and is really only based on monitoring small local changes in the magnetic fields from monitoring sunspots and emissions. Really, the only true warning for a solar storm is to witness the flare, which then gives us either a few days or a little bit less to prepare for the incoming coronal mass ejection before it hits Earth. The effects of these solar storms on Earth's climate have been monitored for a while in history, and despite some correlations, such as when there was the Maunder minimum being a minimum period in solar activity, which correlated with the Little Ice Age in Europe, there has never been a satisfactory model which explains how a reduced solar activity would cause cooler temperatures on Earth. And when we look at the energy output of the sun during solar cycle changes, it actually only changes by about 0.1% of the energy output. So this is not really enough to change global temperatures in such a drastic way. Other explanations for the ice age at that time, the Little Ice Age, include increased periods of volcanic activity, which just happened to coincide with the reduced solar activity. So it's been suggested that increased X-ray and UV emission from the sun from increased sunspot activity might cause minute changes in the Earth's atmosphere, but this is a correlation versus causation issues. or correlation versus causation issue. And so, better understanding this phenomenon is a matter of debate scientifically and really hinges on future work that can theorize a good, predictable model. This brings us to an end on our lecture on the sun and its outer layers and inner layers, and about solar activity and how it affects the Earth.